What if every digital message you've ever sent, every medical scan, every financial transaction, was fundamentally flawed? Imagine a world where the very fabric of information, the bits and bytes that define our digital existence, are constantly under threat of decay, corruption, and outright error. Sounds like science fiction, right? Well, for the quantum computers of tomorrow, this isn't just a possibility. It's their harsh, everyday reality, and fixing it is the biggest challenge in the multi-billion-dollar race for quantum supremacy. Today, we are diving deep into the fascinating, mind-bending world of error correction, from its unsung role in our current tech to its monumental, existential importance for the quantum age, the fierce battle among tech giants, and the profound philosophical questions it forces us to confront. At its core, error correction is about reliability. Think of it like this. When you send a text message, your phone doesn't just send the raw letters. It adds extra information, redundancy, so that if a tiny bit of the signal gets garbled by interference, say, a cosmic ray or a faulty antenna, the receiving phone can still piece together the original, correct message. This silent guardian of data integrity is everywhere. In your hard drive, your internet connection, the memory of your smartphone, even the high-definition video streaming to your screen right now. Without it, our digital world would collapse into an unreadable mess of static and nonsense. It's a sophisticated dance of mathematics and engineering, transforming noisy channels into reliable pathways for information. But here's the kicker. For classical computers, this is relatively straightforward. You can simply make 3 copies of a bit. If one flips, you know the other 2 are probably correct. Simple majority rules. Now, enter the quantum realm, and everything gets weird. Instead of bits that are either 0 or 1, quantum computers use qubits, which can be 0, 1, or a superposition of both simultaneously. They can also be entangled, meaning their fates are linked, no matter the distance. This quantum magic is what gives them their immense power for specific types of calculations, promising breakthroughs in drug discovery, material science, artificial intelligence, and cryptography far beyond anything classical computers can achieve. But this quantum fragility is also their Achilles heel. Qubits are incredibly delicate. They are prone to decoherence, losing their quantum state and collapsing into a classical 0 or 1 due to the slightest interaction with their environment. Heat, stray electromagnetic fields, even a tiny vibration. The slightest whisper can destroy their quantum coherence, turning potential into noise. And unlike classical bits, you can't just copy a qubit without disturbing its state. That's the no-cloning theorem of quantum mechanics. So, our classical error correction tricks are useless. This is where recent breakthroughs in quantum error correction, or QEC, become absolutely pivotal. Imagine needing to correct an error on something you can't directly observe without changing it. That's the QEC paradox. The solution involves encoding one logical qubit, the stable, useful quantum information we want to protect, across many physical qubits. These physical qubits don't just hold the information, they also serve as a collective, self-correcting system. Researchers are developing complex quantum codes, like surface codes or topological codes, that weave entanglement into their structure, distributing the quantum information in such a way that local errors on individual physical qubits can be detected and corrected without directly measuring the precious logical qubit itself. Recent milestones from players like Google and IBM have demonstrated the ability to create logical qubits that are more stable than their individual physical components, marking a critical step towards fault-tolerant quantum computing. Google's work with cat-state qubits and their recent findings on scaling QEC have shown improved performance, while IBM continues to push the boundaries with increasing qubit counts and sophisticated error mitigation techniques on their Eagle and Osprey processors. These breakthroughs are not just incremental, they represent fundamental shifts in our ability to tame the quantum beast. This brings us to the thrilling and high-stakes race for quantum supremacy, or more accurately, quantum advantage, among tech titans. Google, IBM, Intel, Microsoft, and even Amazon with AWS bracket, are pouring billions into building the first truly useful, fault-tolerant quantum computer. Google made headlines in 2019 claiming quantum supremacy with its Sycamore processor, performing a task intractable for even the fastest supercomputers. IBM quickly challenged the practicality of that specific task, highlighting the ongoing debate about what truly constitutes advantage. Regardless of who's leading the theoretical charge, the practical goal remains: a quantum computer that can solve real-world problems faster and more efficiently than any classical machine. The applications are staggering, discovering new drugs by simulating molecular interactions at an unprecedented level, designing novel materials with tailored properties like room-temperature superconductors, optimizing complex logistical problems for global supply chains, and turbocharging AI algorithms with quantum machine learning. This isn't just about faster calculations, it's about solving problems that are currently impossible, unlocking entirely new scientific and technological frontiers. However, this quantum leap isn't without its shadows. The most immediate and widely discussed concern is cryptography. Schia's algorithm, a theoretical quantum algorithm, could break many of the encryption standards that secure our internet, banking, and national security systems today. RSA and ECC, for example. The advent of large-scale, fault-tolerant quantum computers would render our current digital security obsolete. This isn't a future problem. It's a harvest now, decrypt later threat, where encrypted data is being collected today, awaiting a quantum computer to unlock it tomorrow. This has sparked a global effort in post-quantum cryptography, developing new encryption methods resistant to quantum attacks. Then there are the broader ethical implications. What if quantum AI systems become too powerful, too opaque? What about the potential for unprecedented surveillance or the disruption of entire industries? These aren't just technical issues. They're societal challenges that demand foresight and open discussion. If you're finding this deep dive into the quantum world thought-provoking, please hit that like button and subscribe for more explorations into the future of technology. Also, let me know in the comments what other mind-bending tech topics you'd like us to cover next. Beyond the practical concerns, quantum mechanics itself forces us to confront profound philosophical implications. Error correction in the quantum realm isn't just about fixing a flipped bit. It's about preserving a fragile, probabilistic reality. What does it mean for our understanding of information, certainty, and even existence, when the very stuff of computation is inherently uncertain until observed? The act of correcting an error in a quantum system involves inferring information without directly observing the quantum state, a subtle dance with the observer effect. Does the multi-layered redundancy of QEC mirror a deeper redundancy in the universe itself? Some interpretations of quantum mechanics, like the many-worlds interpretation, suggest that every quantum measurement causes the universe to split into countless parallel realities. If we are correcting errors in our quantum computations, are we, in a strange way, selecting a specific branch of reality or ensuring coherence within our chosen computational reality? These aren't just abstract ideas. They highlight how deeply quantum technology intertwines with our fundamental understanding of the cosmos and our place within it. It blurs the lines between physics, information theory, and philosophy. Looking ahead, the journey to a fully fault-tolerant quantum computer is still long, but the milestones are coming faster. Future solutions will likely involve a combination of improved hardware, more efficient QEC codes, and hybrid classical quantum architectures where classical computers handle the error correction and control, while quantum processors perform the unique quantum computations. The goal isn't just to make qubits stable, it's to make them scalable, robust, and accessible. We might see the emergence of a quantum internet, a network of entangled qubits enabling secure communication and distributed quantum computing. The practical takeaways for us are clear. Stay informed, understand the evolving landscape of cybersecurity, and recognize that we are on the cusp of a technological revolution unlike any before. The challenges are immense, but the potential rewards, a deeper understanding of the universe, cures for intractable diseases, solutions to climate change, are even greater. The race to correct reality's glitches isn't just a scientific endeavor. It's a testament to human ingenuity, pushing the boundaries of what we thought possible, one perfectly corrected qubit at a time. Don't forget to like this video if you learned something new, subscribe for more content that challenges your perception of technology, and share your thoughts in the comments below. What do you think the biggest impact of quantum computing will be? And what other tech mysteries should we unravel next?